Hello and welcome to the third lecture of electric machine design using Ansys Maxwell series. In last lecture we covered how to create various geometric shape in Maxwell modeler, edit their dimensions as per the design requirements and other important features that will help us out throughout this course. Building upon that knowledge, in today's lecture we will be diving into an exciting topic: parametric geometry creation using Maxwell 2D modeler. We can say that this is often considered as a first step of the finite element analysis. Now, when we say parametric geometry, we mean that once the geometry is created, its dimensions can be modified dynamically using the parameters or variable whichever we have defined in the Maxwell. This feature makes Maxwell quite a versatile, as it allows us to quickly explore the design variations and optimize the machine performance without redrawing the geometry. Before we begin, it is crucial to identify the key geometric parameters that will influence the machine performance and should be parameterized to include in the optimization process. So as a designer, we must have a clear understanding of the parameter we are planning to vary, since these parameters will directly impact the machine performances. For example, active length, stator outer diameter, rotor outer diameter, magnet length and thickness, other winding related parameters, etc., are very crucial, because even a minor change can significantly affect the performance characteristics like torque, efficiency and losses as well. For this tutorial, we will create a parametric geometry of a surface permanent magnet motor that looks something like this. Here we have identified the design parameter to assign in the stator and rotor. For stator, we will be keeping these parameters, and I have tried to show how those parameters will be measured. Similarly, for rotor, these are the parameters we will be considering. Now, the first step will be defining a geometric variables in the Maxwell 2D. So let us start with adding a new project and a Maxwell design. So new project, I will name this project to be geometry. I'm adding a Maxwell 2D design. Thus also I will name it to be geometry. Now Maxwell has a capability to define the variables in a two different format. One are called as a design variable and the others are called as a project variable. So what is the difference in between those two? So when we say design variable, that is only applicable to the given design, which means if you make a change into that variable, it will be applicable only for that design. Whereas if you are assigning a project variable, so project variable will be applied to all the design it is carrying inside the project. For example, if I have created a stator outer diameter as a project variable, and if I am creating two multiple designs, say one being a 2D, one being a 3D or any other designs, and if I change the active length or the other project variable that I have defined, that value will be applicable for all the designs wherever I have assigned into that. So we have to be careful when to assign the project variable and when to assign the design variables. In this case, we will be assigning only the design variables. So let us start with it. Now, how do we assign the design variables? So as you can see, the moment I click on the, or if I select the geometry design which we have created, on the property window we are not seeing anything, which means currently we do not have any of the design variable assigned. If I want to assign a design variable, I will right click onto that and I will go into design properties. So whenever I'm going into design properties, it will show me a dialog box something like this. And you can see that currently I don't have any of the variables. So what I will do, I will add it. Now here first thing it will ask me is what name I want to keep for that variable. So I will keep, let's say, slots. Now slots, what is the unit type? Now Maxwell is provided with multiple unit types. You can see we have length, we have mass, we have other electrical quantities, even thermal quantities, and all those things. So depending on our variable, we have to pick certain unit types, whichever is suitable to that. Now for slots, we do not have any of the units, so we will just keep it as a none. Say I want to design a 12 slot machine. I will just simply click OK, and you can see that I am able to see slot as a parameter, what is the value of that, and that is the final evaluated value. Now you can see that we have value and then we have evaluated value. So what is the difference between these two? So value means you can directly enter a value, or if you want to define some formula or functions, you can define it over here. So here you will have to give the function or direct inputs, and this will be calculated based on the values you have provided over here. So this is editable, this will not be editable. Now we have further things like description. If you want to add some description, like number of stator slots, just to give an information about what that variable suggests or denotes. Whether you want to keep read only, which means if you don't want to change the value, or if you don't want any other user to change this value, you can make it as a read only. If you make it a read only, whatever the value you have given will stay that only, nobody will be able to change it. Hidden, if you want to hide that variable from the visibility, you can just make it as a hidden. And sweep means whether you want to consider that into a variable study, then you can keep it enabled. So I'm going to keep everything as it is. Now let's say we are going to add all the other parameters that we just saw in our geometry, which we are going to consider. So now let's say first state OD. Now stator OD is stator outer diameter. I'm keeping it for stat underscore OD. I will keep that value currently for 160. Now here unit type and units, we can define it in a two way. One thing is you select appropriate unit type, and from there you drop it down to the values and click OK. And you can see that appropriate unit is coming, and then it should show like this in the evaluated value, like stator. Now this is not required or compulsory. If you want to give the description, you can give it, otherwise it's okay. The moment you will click apply, you will see that on the property window here both the variables are visible. So let's go into it in a detail, and I will just one by one I will apply all the variables. So I have air gap. Now second method is, if you know what is the unit, you have to write it. If you directly write that unit, you don't have to select from the unit type and units. Automatically Maxwell understand and it takes it up. For example this. So you can see similarly I did not selected the unit type and all, but the moment I written the 0.5 mm, it automatically picked it up. So let me write this up, all the values. So you can see that here I have defined all the necessary variables that was required for me. Now here PM angle in electrical degrees, we know that for a full single pole electrical degree will be 180 degree, and we can vary in the dimension of how the pole arc is being taken care using this PM angle electrical degree parameters. Just clicking applying and then click OK. So you can see that now all the variables are visible over here. So since we have now defined all the variables that was required, now we can start with the modeling. So first I will start with creating a very big circle. I will name this circle as a stator. Here I will change this radius. Rather than just a value, I will name this as a stator OD. Now this is very important to keep in mind. Here this dimension is in a diameter, whereas the circle is asking for the radius. So what I'm going to do, I will just divide it by 2. So Maxwell understand this type of a mathematical equation makes us very easy to modify. So now we have a stator ready. What we are going to do, we're going to make a hole into that. So I will just change this as a stator OD by 2 minus yoke thickness. So now we have a dimension of yoke thickness, and now we will be using the options that we have discussed in a previous lecture. So I'm first selecting the stator and then I'm selecting the circle, and I will subtract the circle one from the stator and click OK. Now we have our outer ring or outer yoke of our stator. Now we will be creating a rectangle. I will name this as a tooth so that I can remember that this geometry is used to create a tooth. Here currently, as I can see that this is on the x-axis. So what I want to do is I want to make sure that this tooth is divided in a top half, bottom half equally by an x-axis. So what I will do, I will change this to PM minus tooth width by 2, and x size I will keep stator OD by 2, and y I will keep tooth width. So now we have our tooth ready, but we have to subtract this because here we will be having a rotor. So what I will do here, again I will create one more circle, create rotor OD by 2 plus air gap. Now we have over here, so I will take this one and I will take this one, I will make a subtract. So circle 2 will be subtracted from the tooth, and there we go. So now we have only our one circle. Now you can see that since we have created a straight line of the rectangle, if we zoom into the stator outside, so you will see that my tooth is going a little bit outside from the stator OD, which we will not be having in our realistic geometry. So to avoid this, what I'm going to do here is I will create another circle. I will create it as a stator OD by 2, and this time I will just keep a intersection of this. So now you will see that only the curvature based part is there. So now we have our tooth properly formed. This is only one tooth. We have to replicate it throughout the circumference. So we will do it 360° divide by slots. So you see that we are using the duplicate around axis which we explored last time, and here we are not giving directly angle, but we are giving it in terms of a formula, because we know that if we want to change the number of data slot later on, we should be able to easily do it. So here you can see that immediately it got adjusted and Maxwell is showing highlight of where this component might land. Now currently it is asking for a 2 number. If I want to make it 12, it will show again where all those components will be landed. Now here you can see that we are seeing attached to original object. In last tutorial we did not cover this. Now this is important one. Why? Because how this is going to affect our geometry. So let's say if I do not enable this option, and if I will click it, so you will see that I have each of the component individually created. Okay, and the issue with this is that if I want to change the number of slot later on, I will not be able to change it. For example, let's say if I go over here and if I want to change this value, I'm not able to change it. But I'm doing a Control Z, and let's say we are doing the same operation. I will just keep it over 2 here. I'm doing with the attached to original object, and I'm clicking OK. So you see that this time it created only one master object. There is no another object has been added. Now if I will add it over here, and if I assign this as a variable, I'm able to easily assign it. So whenever you are designing it in terms of a stator, we should always keep it attached to original. Now we'll do another thing, is adding the tooth tip. So here add rotor OD by 2 plus our air gap. We can copy paste also. So I'm just copy pasting, Control C and Control V, and this time I'm just adding tooth tip depth. So you see that we have two different rectangles. I will just subtract one from another, and now we have a ring representing as a tooth tip depth. Now here we will have our slot opening. So what I'm going to do again, I will be adding a tooth. This time I can simply just make a Control C, Control V. Okay, so I will have a tooth 1. I'm naming it as a slot open, just to remember that what this particular geometry has been created for. So you can see slot opening. I'm just going over here, and this time I will just change this value to be slot opening by 2, and this I will name it as a slot opening. So you can see that I have a geometry created, something like this. Now I will just rotate this by 360° divided by slots divided by 2. So we want to rotate it by half a slot pitch, and I will just click OK. So you can see that the whole thing is rotated by that much of the angle. And now we will do a subtraction, and there we go. So you can see now we have our slot opening created. This time we will be creating a unite option and we will create unite. So now you see that we have only a stator component remaining. Everything else is gone under, everything else has gone under the stator component. And if you want to see the operation, you can see all the operation by extending this different model tree, and it will give you idea of how this model has been created. So now as you can see, we have stator ready almost. Only thing is missing the curvature of pole shoe or tooth tip angle. Now here doing this is slightly tricky and we will be requiring a little bit of help from the trigonometry. So what I'm going to do is I will just rotate this geometry by the minus angle. You can keep positive or negative, whichever is suitable to you. And I'm trying to make it in such a way that x-axis is passing through the center of the slot. Now here we will take a help of creating a relative coordinate system that would be presenting something like this and like this. So how do we do? We know that we will create rotated and both, and I'm just pasting it over anywhere. Okay, now this we have to assign it in such a way that every time, even if we change any of the dimension, this coordinate system origin should always land at this corner point. Now how do we find the origin that would replicate this point? So here, how are we going to take help of the trigonometry? So you can see that this dimension, if I take this line, so the straight line is the cosine component. Let me put it over here. Now I have drawn one line over here, say here to here. One moment. And if I take this line from here to here, so this line will become my hypotenuse. This is the cosine component and this is my sine component. So here I know this value, which is rotor OD by 2 plus the air gap plus tooth tip depth, and this is sine component of it. Now this sine component, I already know that this is half of the slot opening. So since I have this value and if I have this value, I will be able to know what will be this angle. So what I can do is I can assign a variable that would represent this angle. We will be assigning a dependent variable that will help us out in creating the angle. So how do we know this angle? We know that it will be arc sine of y by hypotenuse, or say y by z. So same formula we are going to assign over here, our y being the slot opening by 2 and our z being rotor OD by 2 plus the tooth tip depth plus the air gap. So same fundamental we are going to use, and we will create a formula over here. So I will add another formula, add, I am naming it as a, let's say theta 1. Now a sine is the inbuilt function that is given by the Maxwell itself, which represents for the arc sine. I'm going to use root, sorry, slot opening divide by the router OD time plus 2 times the tooth tip depth plus air gap bracket, and that's it. And you will see that automatically it finds the angle. Just clicking apply and click OK. Now let us see if this angle is properly created or not. So if this angle is created properly, and if I put this as a cosine of the z, it should point over here, and the sine of that it will point over here. So this coordinate system origin should land over here. So let us start with that. So I am going to create OD by 2 plus the air gap plus tip depth. So this became my R times the cosine of theta 1. I'm just copying this whole formula, applying same except changing the sign, and z would be 0. So you will see that immediately this point is moved to this condition, so that whatever the formula we have given is correct. So this type of a tip will become quite handy and will be required each and every time when you are modeling the parametric geometry. Now this lines was just for the explanation, so we can remove that. Now only thing we have to do is we have to apply angle over here, but you can see that currently we are asking it in terms of x and y points. So what we can do is, you can see here we have mode. So currently the coordinate system creation mode is in axis and position. So here it is asking in terms of axis and position. We can change it in terms of a Euler ZYZ, and when you change it to ZYZ, it will ask in terms of a angle. Now whichever the angle you are applying, it will change it accordingly. For example, if say I change it to 50 degree, so you can see that theta is rotating along with the y axis. If I add phi, so you can see it is rotating with respect to the z, and if I change the phi, it is changing with respect to the x. So each of the rotation we know. Now we are just going to change with respect to minus tooth tip angle, and you can see that we have angle created at 50 degree, and that's it. We are ready to create our geometry. Now what I will do here is I will create a big rectangle starting from the origin. So position I will keep 0 0 0. I will keep minus because we want to move it on the minus side of the x. So minus stator OD by 2. Similarly for y, I will put stator OD by 2, positive side. Now you see that I have created a very big rectangle, but we don't have to worry about it, as we will be taking care of it in upcoming stages. Now what we'll do, we will move back to global coordinate system again, and for a remembering purpose, if you want to change this name, like say tooth tip CS, so we can know that what is the CS name and we can remember by it. Now I will just create another circle then I will adjust that to be at 0 0 0, radius to be rotor OD by 2 plus air gap. And now I will just select this, and I will just create a subtract. So you can see that now I have cleared some of the part. Now what we are going to do here in this case is we will be drawing one rotated coordinate system like this. So I will select this relative rotated, and I'm just assigning it over here. Now we want to make sure that this coordinate system stays in all the site, like whenever we are changing the number of slot, it should also rotate its angle. So I will again go back over here, and I will just name it as a 0, and this would be 360 degree divided by slots divided by 2. So you know that from here this came over here. Now I can name this as a slot center or tooth center, whichever is feasible to me. I'm keeping it as a slot center CS. Now here Maxwell will not directly allow to cut it from here and duplicate it on the other side, because we want to duplicate this on the other side, but we have to take another coordinate system slightly above this side, and if we will cut with that or split with that, then it will be easily accessible. So what I'm going to do is I will keep this as a working coordinate system, and I will keep as a new coordinate in offset, and this value I will define as a minus C tooth width by 3. And this, now you can see that not anymore at the center, and we can just simply select this rectangle and we will split it out. Now currently you know that it is splitting on this part, so it will keep this part, it will remove this side, but we want this part to be kept, this part to be removed. So first we will change the plane, second we will change the direction, and click OK. So now one side of the tooth tip is ready. We will go to slot center coordinate system, then we'll just go around. This time we want to replicate it on this side, so here we will rotate around the x-axis, and I will keep the angle to be 180 degree, and I want only 2 number, and that's it. Click OK. So this happened for one side of the tooth. Now I will go back to global. Again I will select the rectangle and do the same thing, but this time we will be replicating for all the slots. So 360 degree by slots, click OK, and then you will come over here and assign it as a slots, and there we go, we have all the slots completely proper. And then stator rectangle will make a unite, and you can see that we have our stator ready. This, if anybody wants, we can just move it back to the minus side and click OK, and that's it. We have our stator centered towards the geometry of a tooth. Now since we have created a geometry clear of the stator, we want to add few more things such as a windings and all. So how do we create the windings? Here I will add the few more things. So let's say again I'm creating one circle and I will create stator OD by 2 minus yoke thickness and minus, I will write it as a slot liner. Now you see that the slot liner is not the defined variable. We have not defined it earlier. So whenever we are writing any of the variable that is not predefined, automatically Maxwell will look into it and it will ask us to add the variable. So it is not necessary that you have to always create a parameter list first before going to the modeling stage. You can assign the variable as you go ahead in the process, and wherever you feel like, okay, now I will be needing a new geometrical parameters, you assign it over there. Okay, so let's say slot liner, we want to have a 0.2 mm of slot liner. So you will see that in between yoke thickness and this OD we have 0.2 mm of gap. I will just simply copy paste it. Again I will change this dimension, say rotor OD by 2 plus the air gap plus tooth tip depth and plus the slot liner. So you'll see that I have the geometry over here. Again I will do a subtraction. Now you can see that I have my winding area field. Now here we want to make sure that our winding area stays within this stage. So what are we going to do here in this case is we will create a few offset and few of the rotated coordinate systems. So first let's see, we already have the slot center CS. So what I'm going to do, first thing is I will split this. I will keep positive side and there it is. So you'll see that I have this geometry already available. Similarly, I want to make sure that this is available on this side also. Okay, so this is my slot center and I will select this again, split it. This side I will keep it on a negative side. So I have it ready. Now few more operations we need to do in order to remove this part. So how we will be doing, I will just go to this and I will create another rectangle. So this rectangle I will keep at 0 0 0 only. Y size we will keep stator OD by 2. Sorry, Y size will keep tooth width by 2 plus our slot liner. So you will see that it's slightly increased, and then X size we will extend it up to stator OD by 2 in order to avoid any of the geometrical issues when we change the parameters. So now this is our stator, rectangle and circle. So I will just take the circle, from there I will take this and I will subtract it. Now you can see that I have few more things pending. Here I need to remove it on this side, and here also we have to create a little bit of a gap over here. So this is my slot center CS. We're gonna create a very fine rectangle. So this I will keep again X to be stator OD by 2 and Y we will keep slot liner, and this again we can do a subtract. So now we have only remaining this part to remove. So for that what we'll do, we'll set this slot center from there to tooth tip CS as a working coordinate system. I will take one rectangle over here. I am writing this as a slot liner for the starting point. This I will write stator OD by 2. This also we want to keep positive side of the stator OD by 2. Now we'll move back to global. We'll just rotate it using the z-axis by 360 degree, divide by slots, divide by 2, or say half a slot pitch. We'll click OK. Now I will use the slot center CS. Again I'll just rotate it by x-axis with 180 degree, and I'll just click OK, and we have our cut point ready. So I will just use this, I will do a subtract, and you can see that now our one side of the coil is ready. So I will just duplicate it around the axis using 180 degree. We will use x-axis for now, and this time we need to make sure that we do not create attached to original. This is very important, as when you attach to original, it only creates a one common object for all the bodies. Here in winding we will be assigning positive and negative polarities for a different conditions. So every time we have to select different bodies, and it should be replicated as a different object. So we will be just keeping it as a two object, not attached to original case, and there it is. So you can see this is, let's say I'm naming it as a C1, this I will name it as a C2, and we have our C1 C2 ready. I will again further copy it out, 360 degree, divided by slots, and this time we have a 12 slots, so we'll replicate it for the 12 bodies and click OK. Now we have our geometry all prepared. Let us change a little bit of coloring, and this I like to keep it something that looks like a copper winding, and there we go. So now we have our stator assembly ready. Pending is our rotor. Again we'll use the rotor, creating the circle. I will create rotor OD by 2 minus PM thickness. I will copy paste this geometry. I'm naming it to be rotor. Then I will name this to be rotor ID by 2. Now this rotor minus rotor 1, we have our rotor body. Just changing the color for a better visibility. Now I will just again create, copy paste, and this, let's say I'm naming it as a PM, or say PM1. So this I will name that as a stator rotor OD by 2, and this I will name it as a rotor OD by 2 minus PM thickness. So this we have our whole ring ready. Now this time we have to create a cutting section to create a single magnet out of this magnet ring. Now how do we do that is, we know that for any number of pole, 360° divided by the number of poles, that would be the maximum pole angle, or 780° electrical that pole will be able to occupy. So here again, using the same right angle triangle rule, I am going to find what will be the y point over here. So same way we will be creating a coordinate system. So here let's say we want to create offset only. So this we will name it as a PM upper split CS. You can name it as per your suitability. I'm just giving you an idea so that we can remember that what that particular coordinate system is created for. So this I will name it as a rotor OD by 2 minus PM thickness times the sine component we have to take, and this time PM angle in electrical divided by number of poles, and we are, so now you see that the number of pole we have not defined. So say we are going to create a 10 pole machine, and it automatically adjusted. Similarly, I can copy this whole out. I'm going to create same coordinate system on the negative side. This time you can see that reference I forgot to change it into the global, so I can change it over here. We don't have to delete it and recreate it. You can just change it to the reference, and I will just change this out, and this time I will keep minus. Now since we have coordinate system ready, let me just rename it. I'm naming it to be lower. Now this, and this is our PM1. I'm going to split it. I'll keep on the positive side. Okay, again I will change this coordinate system. This time I will keep it on the negative side. Click OK. Now you can see that we are still able to see two poles. I will split this using YZ plane. This time I will keep only a positive side, and there we go. We have our one pole or one magnet ready. Now we can just simply create a copy of 360° divided by the poles, that would be the angle, and 10 pole is what we are looking into, and we'll just click OK, and we have our model ready. Let us change a little bit color, so you can see that now this geometry is ready and we have all the parameters. Now once we are ready with the parameter or parametric model, it is important to know that whatever the values we have given, are they consistent with the value what we have derived. So let's say stator OD we have told it to be 160. Now we have to verify that these values are staying consistent if I am changing this variable. So here diameter is 160 mm. So what I'm going in edge selection mode. I will select this edge, go to measure and edge, and you can see that this is 160 mm. That means this is correct. Then we have a yoke thickness which is 8 mm. So if I want to measure the yoke thickness, I will zoom in over here. So yoke thickness is this and this distance. So this is 8 mm. That means this dimensioning is correct. Let's say tooth width, measure and edge. So 10 mm, which we have defined over here. So similarly, we should be measuring all the parameters one by one to check the consistency. 0.5 mm air gap, 0.5 mm air gap. Then the thickness of the magnet, 5 mm. H. So say we have 50 mm diameter. So this way we have to one by one cross check that all the variables are within the proper alignment. Now after that, again let's say we are changing this value tooth width to 12 mm, and you will see that immediate change in the geometry should be visible. Again let's measure that. Now this time tooth width should show 12 mm. So again I am measuring the distance and it shows 12 mm. That means the geometry is staying consistent with the required diameter. Okay, so this is how we are generally making the geometry. Apart from this geometry, we have to do a slight additional modeling in our Maxwell model to make it viable for the finite element analysis. So what we have to do is we have to add a rotational band and we have to create a region. Now what is that? So currently you are seeing that only we have a geometry. So Maxwell will automatically not understand that within this range we have to mesh on, we have to do all the analysis and everything. So we have to assign some boundary conditions such a way that Maxwell can understand that okay, within this constraint or within this region I have to do all the solution, all the meshing and everything. So in order to complete that, we have to create some boundary box that would make Maxwell understandable. So here we can simply take one circle and you can just simply name it to be a region. This you can change the color to white. I will keep always that to be a transparent so that it doesn't affect my geometrical view. Now as I had mentioned earlier, we have to create a rotational band also. So we know that this rotor is going to be rotate. Now here Maxwell will not be able to understand just by the naming that okay, it is, if it is named as a rotor it will be rotating and all. For Maxwell this is just a common geometry that it has to mesh and it has to solve according to the given excitations and boundary condition, etc. So we have to make Maxwell understand that we will be making a rotational circle in which all the objects will be rotating. Another thing which we will be making is we will be dividing this band in a 3 different layers or 4 different layers, let's see. So what we will be doing, we will be parameterizing that as well, and the significance of that we will be discussing when we are into the meshing tutorial. So let me just create it out. I can use this. I am naming it as a band. So here I have to make sure that this band is right at the center of the air gap. So what I will do, I will name this as a band and I will define the variable to be rotor OD by 2 plus half of the air gap we want to keep, so 0.5 times the air gap. So you can see that the circle is lying right into the center. This again I will keep white and this I will keep completely transparent. Now you see that the band and region I kept as a completely transparent. The reason is that geometrically that is not existing. So it is just representing it as a understanding, or making the software to understand the quantity. Otherwise, in reality, we will not be having that any of the band or region in our testing environment. So just to avoid confusion, I'm just keeping it to be a white colored and completely transparent. Now, since I mentioned that we will be dividing it in a 4 layers, so here you can see that with one band we have 2 layers. So I will just copy paste 2 times. So this band 1, I will name this as a band in. This I will name it as a band out. Band ins, I will keep it at 25% of the air gap, and this I will keep it at 75% of the air gap. Now you can see that we have a 4 layer of air gap division. Now this is actually very important when we are doing a simulation, so as to get accurate results and avoiding the mesh noises, etc., which we will be later on discussing when we are into the meshing stage and all. But always try to keep a habit to model up to this. Now we have our geometry ready. Only thing you can keep some extra thing is, like, if your stator OD is also going to change in your geometry, you can try to parameterize the region also, like stator OD times 1.1, sorry, stator OD by 2 times 1.1. So generally 10 to 15% of the extra space you can keep it. I would recommend you to keep in between 10 to 20%, whatever feels okay to you. This is again purely a user's choice, but 10 to 20% is a sufficient margin. We're going to save this, and now our geometry is completely ready. So that's it for today's lecture. Thank you for watching, and let me know if you have any queries or concern for this model. Cheers.